In the last video, we learned about measurement. And a measurement is basically a quantitative observation that's being described by a number and a unit. And the system of units that scientists use today is called the International System, or SI. However, in chemistry, measurements can be a very large number or a very small number. In this video, I'm going to show you how to rewrite those numbers in the form of scientific notation. So you don't have to write all the digits and still express the same values. So the purpose of writing a scientific notation is to express a very large number or a very small number in a form that we don't have to write all the digits to show the values of that number. Before we look at scientific notation number, let's look at the standard form number. This is the form of numbers that we see in our daily life. Basically, it's a number written with all the digits and their place values, or its place values of each of the digits. So I have 123.407. We have 6 digits that make this number, and each of the digits represent a specific values. For instance, this one represents a hundredths, this one represents the tenths, and this one represents the ones. Then we move down. After the decimal, this fourth represents the tenth, this 0 represents the hundred, and this 7 represents the thousandth. But using scientific notation, we can express the same number in a different form. And if we look at the notation of a scientific number, there are 2 parts. The first part is called the coefficient. And the requirement for the coefficient is this. The coefficient must be greater than or equal to 1, but it has to be less than 10. Just like 3.05 is greater than 1, but it's less than 10. The second part, which is the most beautiful part of the scientific notation number, it is the power of 10, or we call it the exponent. The base will always be the power of 10, but this exponent right here represents how many times 10 times 10 to itself is going to be. So in this case, if I have this number, it's basically saying that 3.05 times 10, there are 3 of them, times 10 times 10. That's where we get 10 to the power of 3 going to be. And the beauty behind of 10 is that each of the 10 represent a decimal place. So 1, 2, 3. And that will give us 3050. And that is the beauty of having an exponent with a base of 10. Now let's look at specific example, how we can change standard form number to scientific notation. And it's all based on this beautiful acronym. And that acronym is LARS. It's based on the concept of moving decimal, you have to change the exponent. Because we have to keep the values of the numbers stay the same. And LARS is basically representing L is for left, A is for add, so they come in pairs. So when you move to the left, you add to the exponent. And R is moving to the right. S is subtract from the exponent. So LARS, keep that in mind. So the concept again is when you move the decimal, you change the values of the decimal part, just like we did here, right? But you have to keep the values of the entire number the same, so you either add to or subtract from the exponent. So that way, the values of the numbers stay the same. Now let's look at the first part, the LA part, which is move to the left, you add to the exponent. Okay, let's do some example with the LA part. Move a decimal to the left, you add to the exponent. And the explanation behind is this. If you move the decimal to the left, the coefficient number gets smaller. Let's use an example to clarify this. I have 5,000 times 10 to the negative 5th grams NaCl. Here, if we look at the coefficient part of this number, the decimal is at the very end. Because if the decimal is someplace else, it would not be 5,000 anymore. So the decimal is at the end. And why am I moving to the left this way? Because we have to make the coefficient again. It has to be greater than or equal to 1, but less than 10. And 5,000 is a lot more than 10. So how many decimal places do we have to move? 1, 2, 3. So the total of 3 decimal places that we had to move. And what did we just do to the values of 5,000? We basically make that values less by 3 decimal places. Now, if we look at the structure of the scientific notation, there are 2 parts, the coefficient and the exponent. In this case, the values of the coefficient decrease. We have to counteract by adding more on this side to keep this balanced. So what we're going to do is we're going to do the opposite. This decreased by 3, we're going to add it by 3 to the exponent. So negative 5 add 3, that gives us a total of minus 2. So our answer to writing this number in terms of scientific notation would be 5.000, see the decimals right there now, times 10 to the negative 2. Now let's use a calculator to prove that this method is actually valid. I'm going to plug in this number, 5,000 times 10 to the negative 5th, and give us 0.05. Now let's plug in this number, and the values is going to be the same. 5.000 times 10 to the negative 2. And look at that. It's the same value. But the number look completely different. Let's do another example. I have 10.0 times 10 to the 3rd liter of H2O2. So I have to move the decimal, so the coefficient is going to be greater than or equal to 1, but less than 10. So in this case, it is exactly 10, so I move this way by 1 place. So now that decreased the values of the exponent by 1 place. So I had to do the opposite to the exponent by adding 1. That gives us 1.00 times 10 to the, what is 3 plus 1? That gave us 4. And that is our answer. Let's try another one. I have 500.05 times 10 to the 5th moles of glucose. And because 500 is greater than 10, I have to move the decimal to the left. So that way, 1, 2, there you go. I have 5 now. So 5 is less than 10, but it's greater than 1. So that'd be good. But I make the values of the coefficient less by 2 decimal places. So minus 2. And I have to do the opposite to keep the values of the whole entire number the same. So I'm going to add 2 to the decimal. So 5 plus 2 give us 7. So we have 5.0005 times 10 to the 7. And that is the LA part of large. Now let's look at the last part, which is RS. And guess what RS represents? RS is basically move the decimal to the right. You are going to do the opposite, which is the S. You subtract the exponent. So RS, R is right, S is subtract. So let's look at how is that going to work with some of the example we have here. Let's use one of the examples to explain this RS part. I have 0.005 times 10 to the negative 5th grams of NaCl. Now, why am I moving to the right in the first place? Notice how the decimals are here, and this number is a lot less than 1. So we have to move this direction to make it greater than 1, but less than 10. By how many places? 1, 2, 3. Because if I stop right here, that only give me 0.5, which is half of 1. So I move right here, that gives me 5, which is less than 10, but greater than 1. So by how many places did I just increase the values of this coefficient? I just increased it by 3 places. And guess what I'm going to do to the exponent? I would do the opposite of it, which is I'm going to subtract from the exponent by 3 places. What is minus 5 minus 3? That gives us a total of minus 8. So we have 5 point, which we don't have to write all the 0 in front. That wouldn't make any sense. So 5 point times 10 to the negative 8. Let's use our calculator to prove this. I'm going to plug this into the calculator. We have 0.005 times 10 to the negative 5 and give us a very small number. And notice how we have 5 point times 10 to the negative 8, which is exactly as this one right there. And we just proved that this method is valid. Then, let's do another example. I have 0.010 times 10 to the third liter of H2O2. So this number is a lot smaller than 1, so I have to move this way to make it larger than 1, but less than 10. 1, 2. There you go. I have exactly 1, but I increased the coefficient by 2 places. So I would do the opposite to the exponent, minus 2. So I minus from the exponent, that gave me 1, because 3 minus 2 gives you 1. So we have 1.0 times 10 to the 1. Let's do another. Here I have 0.00505 times 10 to the 5th moles of glucose again. Because this is a lot smaller than 1, we have to move the decimal this place to make the values of the coefficient greater than or equal to 1 by less than 10. So 1, 2, 3. There you go. We have 5.05. So I just increased the values of the coefficient by 3 places. And I would do the opposite to the exponent to keep the values of the entire number the same. So I would do the opposite, which is minus 3. So 5 minus 3 gave us 2. So our answer is 5.05 times 10 to the 2. Both. Notice throughout all the example, I did not rewrite the unit and the chemical because there are no changes to the unit and the chemical. They just stay the same. Basically, you just copy it down. And that is how you change a standard form number to scientific notation.